Yo, what is up YouTube? In this video, let's take a look at how we can solve this PDE. We want a solution in the form u of x and y for the following. So this is the Laplacian. This is delta u equals 16u. So over here we have two x partial derivatives and two y partial derivatives. And then we were given a couple boundary conditions. This one right here is nice. Those are two homogeneous boundary conditions and Dirichlet boundary conditions at that. Then we have another homogeneous boundary condition, and this one will work out at the end. And we're given this hint. So we're given that the integral from 0 to pi of sine squared of 3x dx is equal to pi over 2. So it's likely that we'll have something like that pop up. The first step we always do in solving these kind of problems is apply separation of variables. So u of x and y is going to be equal to some capital X of x times y of y. And let's go ahead and just plug those into the equation. So d squared u over dx squared becomes x double prime of x times y of y. This one becomes plus x of x times y double prime of y. And this u over here, this is all going to be equal to 16 times x of x times y of y. Now something cool that we can do when we use separation of variables is divide by, let me get the pointer. We'll divide by x of x times y of y on both sides. And the reason that we're able to do that is because we want x of x multiplied by y of y to not equal 0. If it was 0, that'd just be a trivial solution, and all of those get superposed in anyways. So we're going for non-trivial solutions, so we can go ahead and divide by x of x and y of y. That leaves us with the following. We get x double prime of x over x of x plus capital Y of y double prime over y of y is going to be equal to 16. Now, this is where we get to the separating part. We're going to separate the variables so that there's only an x dependence on one side and only y dependence on the other side. So I notice I have some boundary conditions in the x variable that are really favorable. So I'm going to try and make the x equation as easy as possible. So let's see what we can do there. So to do that, I'm going to drag over the y double prime of y to the other side. And this will give us x double prime of x over x of x is equal to negative y double prime of y over y of y times, well, not times, it's going to be plus 16. And since we have x dependence and y dependence, the only way these things are going to be equal is if they're equal to a separation constant. Let's go ahead and call that mu for the time being. Okay, so now what we've essentially reduced this PDE into is two ODEs. We have a x ODE and a y ODE. ODE stands for ordinary differential equation. For the x ODE, we have x double prime of x is equal to mu times x of x. For the y ODE, we have 16 minus mu is equal to y double prime of y over y of y. We could drag this y of y to the other side, but for the time being, let's go ahead and focus in on this x ordinary differential equation. So because we have boundary conditions in x, specifically Dirichlet boundary conditions, that's to say u of 0 comma y equals u of pi comma y is equal to 0, and that's given here in this problem. These are called Dirichlet boundary conditions. When we have this kind of boundary condition, mu is going to be always less than 0. So let's say that mu is equal to some negative lambda squared for some lambda greater than 0, and this gives us the general solution to the ODE. We have x double prime of x is equal to negative lambda squared x of x. And this is something that was learned very well in ordinary differential equations. And we use it quite a bit in this class, so it's something worthwhile getting used to. We have this negative coefficient and it's squared. So the solutions are going to be x of x is equal to a times cosine of lambda x. A is an arbitrary constant, plus b, another arbitrary constant, cosine of lambda x. Now, we have the solution. What do we do from here? Well, let's go ahead and apply some of those boundary conditions. we said u of 0 comma y is equal to 0. So we said u of x and y equals x of x times y of y. So u of 0 comma y corresponds to x of 0 times y of y. This is equal to 0. We don't want this bit to be 0 because if that was 0, we'd end up with trivial solutions. But it's okay if just for one point, x is equal to 0. So this simplifies down to x of 0 is equal to 0. Sweet. What does this do for us? Well, let's plug it into our solution, our general solution. We have x of 0 is equal to a cosine. If we plug in x is 0, we get cosine of 0 plus b sine of 0. Sine of 0 is 0, so this doesn't matter. And this is equal to 0. Cosine at 0 is 1, so we have that a is equal to 1. All right. Oop, not a is equal to 1. A is equal to 0. So that term disappears, and we can update the value of our x solution. X of x is now equal to b sine of lambda x. Now we go ahead and do a similar thing. We had our boundary condition u of pi comma y is equal to 0. So this becomes x of pi equals 0. So we have b sine of lambda pi is equal to 0. And so we don't want this coefficient to be 0 because then x would be 0 for all for everything and we get trivial solutions, but we want this sine of lambda pi to be equal to 0. How can we do that? So lambda pi has to equal n pi because sine of n pi equals 0 for all n in the natural numbers. So this means lambda is equal to n, and this also means that mu, since we said mu is equal to negative lambda squared, equals negative n squared. All right, so now what we have is some solution x sub n of x because we have a whole bunch of these solutions for different values of n, and it's going to be equal to b, and these coefficients, who's to say they can't be different for each value of n? We have some b sub n times sine of lambda. Lambda was n, so we get nx. Let's hold on to this for a second. We got this solution, and now we can take a look at what we do for the y ODE. So I'm going to go ahead and copy and paste this. So we just said that mu is equal to negative n squared. So we can update this equation to y double prime of y is equal to y of y multiplied by 16. We have a negative here and a negative here. That becomes plus n squared. Now, I usually like to write these in front. I don't know why I wrote it like that. Perfect. And this solution, here we have something that's positive out front of y. So instead of sines and cosines, we get hyperbolic sines and hyperbolic cosines. So here we go. The general solution here now is y of y is going to be equal to, let's use, instead of a and b, let's use c and d. So c cosh of the square root of 16 plus n squared y plus d times, and these are going to be all sub n again because these are dependent on the value of n. So d sub n times sinh of root 16 plus n squared y. Now we had another, a really cool value here. Let's take a look. It says u of x comma 0 is equal to 0. So u of x comma 0 equals 0 equals x of x times y of 0. So we have y of 0 is equal to 0. So let's go ahead and plug that in. And we get y of 0 equals cn cosh of 0 plus dn sinh of 0. Well, sinh of 0 is 0, so that goes to 0. And cosh of 0 is 1, so we get cn is equal to, and we said this whole thing was equal to 0. Cn equals 0, and that term goes away. So now we have y sub n of y equals d dn sinh of root 16 plus n squared y. And now we're at a place where we have to do something a little bit different. So now let's combine these two together because we have one last boundary condition to apply. this u of x comma pi equals 3x. And we can't apply that the same way we did here. We have to apply that when we're doing our Fourier series. So let's see what this looks like. We have the solution u sub n of x and y is equal to x sub n of x multiplied by y sub n of x. So this is going to be equal to b sub n sine of nx multiplied by d sub n sine h hyperbolic sine of root 16 plus n squared y. And now these two coefficients, these are both arbitrary. Let's go ahead and multiply those out, and I'll call this alpha n. So if we wanted u of x and y, we would sum all the values of n because they're linearly independent solutions. N equals 1 because remember, it's for all n in the natural numbers. We start at 1, we go to infinity, and we do alpha sub n of sine, or alpha sub n times sine of nx multiplied by sinh of root 16 plus n squared y. Now we need to apply our last boundary condition. That was u of x comma pi is equal to sine of 3x. And so this is going to be equal to the sum, n equals 1 to infinity, of alpha sub n sine of nx times hyperbolic sine of root 16 plus n squared y. And so what do we do now? Well, we apply the Fourier equation to solve for this coefficient, and we group together these two things, and we can solve for a sub n. So we have that a sub n multiplied by hyperbolic sine, and sorry, this y over here, this becomes a pi. Hyperbolic sine of root 16 plus n squared times pi is going to be equal to 2 over pi times the integral 0 to pi of sine of 3x multiplied by sine of nx dx. Now, these are orthogonal unless n is equal to 3. So if n is not equal to 3, then this turns into 0. If n equals 3, this becomes 2 over pi times the integral 0 to pi of sine squared of 3x dx. Remember in the question, we were given the hint that the integral from 0 to pi of sine squared of 3x dx is equal to pi over 2. So we have 2 over pi times pi over 2. That's equal to 1. We have 1 equals alpha sub n times sine h of root 16 plus n squared pi. So alpha sub n, and remember, now that we know n is only equal to 3, this is basically alpha sub 3 is equal to 1 over sinh of root 16 plus 3 squared pi. And this is cleverly chosen. This is 16 plus 9 square root equals root 25, and we're left with 5 pi under the hyperbolic sign. So we get alpha sub 3 equals 1 over hyperbolic sine of 5 pi. Now returning to our solution right here, because alpha sub n is only non-zero when n equals 3, we get alpha sub 3. This sum truncates to alpha sub 3 times sine of 3x times sine of root 16 plus 3 squared y. And alpha sub 3 we just solve for to be right here. And so u of x and y is equal to sine of 3x times hyperbolic sine of 5y over hyperbolic sine of 5 pi. And that's the final solution to this ODE. And if you looked at the thumbnail to my video, I actually graphed that. And I might put up a graph like right here and show you what it looks like. But it's pretty cool stuff. So if you watch this long, I'm happy to share all this stuff with you and hope you liked it. Bye.